could induce puberty in boys who had not undergone puberty just as effectively as testosterone replacement therapy. And it so happened that the journal that Wise Traditions was coming out with a men's health journal in the next month or two. She asked me to write an article about it. Soon after that, I wrote a book review of the China study, which was pales in comparison to what Denise finally accomplished about 5 years after the fact. And my first real major research article for the journal was Dioxins in Animal Foods, a Case for Vegetarianism. And that also dealt with vitamin A because it largely was arguing, or at least in part was arguing, that vitamin A is very protective against dioxin, which is an environmental contaminant. But it was really over the course of the end of 2005 through the beginning of 2007 that I started putting together what I'm going to talk about today, which is the idea that vitamin A doesn't just act by itself, and vitamin D and vitamin K, these vitamins don't just act by themselves, but they actually cooperate together in important processes, and they're needed together. And when you have toxicity from one vitamin, it's not because you have too much, but it's because that balance is thrown off. And so what we want is to get all of these vitamins together so they can cooperate and synergize to produce health. And you want to avoid cases of imbalance where you get problems. In 2005, at the Wise Traditions Annual Conference, we had a very distinguished guest speaker, Noel Solomon, who was involved in vitamin A fortification in Guatemala. And of course, in third world countries, you have serious problems with vitamin A deficiency. You can actually get deficiency so bad that people have irreversible blindness. So these vitamin A fortification problems, obviously we want to get our vitamin A from food. In this case, they're fortifying sugar with vitamin A, but it's actually a life-saving preventative program in Guatemala because the alternative is blindness. So in any case, Noel Solomon gave his talk, and after his talk, some people asked him about cod liver oil, and he said that cod liver oil would make your bones shrink. And this was concerning because basically from a Weston price perspective, the best source of vitamin A is liver, and vitamin D you get a lot from the sunshine, but cod liver oil is greatly esteemed in this community, not only because Weston Price used it as an important part of his tooth decay reversal program, but because this is one of our best sources where you can get vitamins A and D together. So when people heard that cod liver oil would make your bones shrink and you would sort of go whoosh and kind of implode on yourself, this was deeply disconcerting to some of the people who were using cod liver oil, and Sally asked me to look into it. And I'll discuss that shortly. And just as you'll see, over the course of the following year, this evolved into writing about the opposite pole of that spectrum, what happens when you have vitamin D toxicity, and then eventually to this spring 2007 article where I argued that the activator X that Weston Price claimed he had identified in 1945, saying it was a new undiscovered vitamin, was actually vitamin K2, and that was where the synergy of these three vitamins really tied together. So moving forward, the idea that cod liver oil would have so much vitamin A that it would make your bones shrink came from some epidemiological evidence that was conducted in Sweden. And we should keep in mind that Sweden is quite far north, and people don't get a lot of vitamin D in the diet. They don't get a lot of sunshine exposure up there either. So these people tend to be very deficient in vitamin D. And what this found was that 5,000 IU of vitamin A or more per day was associated with an increased risk of fracture. And this was in the late 90s, and this was the beginning of the idea that too much vitamin A will cause osteoporosis. And so I started looking into this, and as it turned out, there were numerous epidemiological studies that followed this. And of course, as we heard in Denise's talk, and as everyone should know, correlation doesn't necessarily mean causation, right? So that's important to keep in mind. But on the other hand, when you have a correlation, it could reflect causation. So it should always give you pause and a reason to investigate why that correlation might be there. And so epidemiological evidence continued, and as it turned out, it wasn't very consistent. Some showed an increased risk of fracture, some didn't show that, some showed that there seemed to be an optimal vitamin A intake where you consume so much and it improves your bones, and you consume more and it doesn't. And one of the things that stood out was some of the studies where there was no association between vitamin A and risk of fracture were in countries like America, where people were actually getting more vitamin D. And you might say, well, everyone's deficient here, but if you compare a lot of Americans to Sweden's, oftentimes Americans are getting more vitamin D. So that was an interesting thing. But what was really interesting was this original Swedish study eventually became a dissertation project for a woman named Sarah Johansson. And I read her doctoral dissertation on this. And she actually made the point that Swedes tended to be very deficient in vitamin D. And she pointed out that there was a body of scientific literature showing that vitamins A and D could have antagonistic effects, synergistic effects, additive effects, different types of interactions. And she actually suggested that the reason vitamin A was harmful in Sweden was because vitamin D intakes were so low. Unfortunately, I thought she was sort of gliding along the surface of the gold mine here, and she eventually, still concluded that people were taking in too much vitamin A. But I think what the gold mine that she was gliding along on top of was what I'll get to soon, which is that you can't really say too much vitamin A or too much vitamin D, but you have to look at it in the overall context. Maybe 5,000 IU of vitamin A is harmful when you're very deficient in vitamin D, but maybe even more vitamin A than that is beneficial when you have all of the vitamins cooperating together. So I decided to take a look at the research that Sarah Johansson had cited in her doctoral dissertation about the interactions between these vitamins. And as I pulled up those papers, I found references to studies going back even further, back into at least as far back as the 1930s. Vitamin A would cause bone loss, which of course is consistent with the idea that vitamin A causes osteoporosis. But if you gave the animals massive doses of vitamin D, it would offer complete protection. So if you had both vitamins there, you didn't get any negative results. On the other hand, massive doses of vitamin D would cause soft tissue calcification. So for example, kidney stones, bladder stones, and stones in other tissues, calcification of blood vessels, calcification of the urinary valves. But if you gave massive doses of vitamin A, you did not get that negative effect. Further, studies showed that even modest doses of one vitamin would seem to deplete the stores of the other. And this would suggest possibly that perhaps they're being used together for something, so that you store vitamin A in your liver, you get more vitamin D, and all of a sudden that vitamin A is being mobilized from your liver and is starting to do other things. And finally, these interactions occur even if vitamin D is provided by ultraviolet light, where both vitamins were given by injection. And this is incredibly important because it seems that many people's first instinct is to say, well, you just have this interaction because when you get too much of one vitamin, it decreases the absorption of the other. But this fact that the interaction persists even when the vitamins are given by ultraviolet light in the case of vitamin D, or by injection in the case of both of them, shows that it's not something that is happening in the intestines, but it's actually some kind of interaction that is happening internally. And so the picture that began to emerge was that, from the animal studies, was that if you have a severe imbalance between vitamins A and D in favor of vitamin A, so you have way too much vitamin A and not enough vitamin D, then this appears to cause a dysregulation in the accumulation of minerals. In particular, you have elevations of phosphorus and a depression of the blood calcium level. And although it's not clear exactly why bone loss ensues, perhaps because the low blood calcium is drawing calcium from the bones, although that's not entirely clear. But this basic idea of this imbalance seems to suggest that if we go back to these foods, you don't want to say that liver is the bad food and that sunshine or vitamin D supplements are the good thing to get, and that cod liver oil is bad because it contains vitamin A. The picture that emerges is that it's probably great to eat liver if you get a lot of sunshine, and if not, maybe you want to take cod liver oil and get both of these vitamins. But that's not what people were saying. People were starting to say, as people were starting to say that vitamin A is bad, people were saying vitamin D is the next best thing, Everyone should be taking vitamin D supplements and sunbathing, and everyone should be not eating liver, not taking cod liver oil, staying away from vitamin A. And so the possibility that we would get an imbalance in the opposite direction was starting to emerge. So the question arises, are we simply repeating an historical mistake? Because the other thing that I found as I looked into this older literature was that all of this had already happened. So, for example, when vitamins A and D were first discovered, it wasn't known that they were two separate vitamins. It was known, they were just called, together their properties were called fat-soluble A. And the first thing that was noticed was that if you didn't have animal fat in the diet of a growing animal, the animal would stop growing. The second thing that was noticed was that in vitamin A deficiency, you would get this disease called xerophthalmia. And basically what happens is when you have a severe deficiency of vitamin A, your eyes stop producing mucus, your eyes dry out, they get vulnerable to bacterial infection, and then this maldevelopment is exacerbated by the bacterial infection, and you get severe ulceration that can lead to irreversible blindness. And cod liver oil was shown to protect against this. And then on the other hand, you had the disease of rickets, which is bowed legs and excessive production of non-mineralized bone matrix. And this was also shown to be prevented by cod liver oil. But the key finding was that eventually they found that you could heat cod liver oil and it would destroy the vitamin A, so it wouldn't protect against eye diseases, but it would leave intact the vitamin D, so it would still protect against rickets. And that's how it was realized that there were actually two different vitamins, which were eventually named vitamins A and D. But people started realizing, hey, a lot of people have rickets, and this xerophthalmia is really, really rare. And they also started realizing that a lot of the animals who weren't growing when they had vitamin A deficiency actually had infections. So they started to say, maybe vitamin A is not that important, this xerophthalmia is really rare, maybe that's not really important, but rickets is really common. So what we need to do is start using vitamin D. The reason cod liver oil is so great is because it's loaded with vitamin D. And vitamin A doesn't really matter that much. Who has xerophthalmia? So as this idea that you could replace cod liver oil with vitamin D supplements, which were becoming available when they started understanding how to synthesize vitamin D2. At the same time, a group of researchers was doing some experiments with dogs and later rats, showing that vitamin A actually had more important properties that were being overlooked. Their first experiment showed that if you raised dogs on olive oil, which didn't contain either vitamin, you got soft bones and bronchial pneumonia, so infection. And if you raised them on butter, which in their case only had vitamin A, of course butter also has vitamin D if the cows are out in the sunshine, but in this case the butter was only rich in vitamin A. They got the soft bones, but they didn't get the pneumonia, they were free of infection. On the other hand, if they got cod liver oil, which had both vitamins, they had well-mineralized bones and they were free of infection. So this seemed to indicate that vitamin A protects against infection in general, and that vitamin D is important for mineralization. When synthetic vitamin D2 came out, they refined this experiment using it, and they performed a similar experiment in rats with a vitamin-deficient diet where they got infections of the tongue, throat, eyes, lungs, gastrointestinal tract, so major infections all over. If they added vitamin D2 to it, it hastened the onset of infection. So again, we're seeing some type of interaction here. If they added vitamin D and vitamin A, there was no infection, and if they only added vitamin A, there was no infection. So they concluded, the importance of vitamin D has attracted great attention recently, and it has even been suggested that preparations of vitamin D can be safely substituted in the late 90s and early 2000s. The work above describes shows that this teaching is erroneous, and that although vitamin D controls probably absolutely the calcification of bones and teeth, it has no direct power to promote resistance to infection in the same way as vitamin A. If a substitute for cod liver oil is given, it ought to be at least as powerful as this oil in its content of both vitamins A and D. So the pendulum swung towards vitamin D as the important vitamin, and now this group was saying what we really need is a balance. However, if you look at the title of the paper, vitamin A is an anti-infective agent, they were essentially enabling the pendulum to swing the opposite way so that people would say, vitamin A is the anti-infective vitamin. And what happened was numerous studies were done on cod liver oil showing that cod liver oil protected against the common cold, for example. I'll show you the slides in a minute. And this allowed people to say, it's the vitamin A in the cod liver oil that's doing the trick. So for example, in this study conducted in the 1930s, they showed that cod liver oil reduced incidence of common cold about 30%. And when they looked at hours missed from work, it cut hours missed from work in half. And cod liver oil, up until the time of World War II, the importation of cod liver oil increased enormously, basically until antibiotics replaced interest in cod liver oil as the solution to infections. And cod liver oil was considered to have saved American industry millions of dollars, which of course is probably billions or more now, because of saving time from lost work because of supplementation of cod liver oil. And also I should point out that cod liver oil is also shown to cut measles mortality over in half. If we blow this up, the difference becomes even more clear. And this, as an interesting historical note, was also the same type of thing we were seeing as they were testing antibiotics, showing that it could do the same thing. In any case, interest in vitamin A as the anti-infective part of cod liver oil led people to say, hey, why don't we use halibut liver oil, which contains all the vitamin A that cod liver oil has, but it doesn't really have any of the vitamin D. So is vitamin A is the anti-infective vitamin. Pendulum had swung in the opposite direction. The problem was the trials testing halibut liver oil instead of cod liver oil didn't work. So this fellow named Erwin Speisman in 1941 decided to say, maybe what you need to prevent the common cold is vitamins A and D together. So he published this paper called Massive Doses of Vitamins A and D in Prevention of the Common Cold. And they gave 50 chronic or frequent cold sufferers who tended to get colds 7 or more times per year, ages 7 through 49, between 9 and 40,000 IU of vitamin A, so way more than they're saying causes osteoporosis now, or 120 to 300,000 IU of vitamin D, or both, during the period of September through June, so the colder part of the year, for 3 years in a row. And what they found was displayed on this chart, where the blue bars represent no effect, and you can see that for 100% of the subjects, vitamin A alone had no effect, vitamin D had no effect, but when they were combined together, in the vast majority of people, represented by the red bar, had reduced incidence or severity of the common cold, or represented by the green bar, were completely free of the common cold. On the other hand, he also looked at symptoms of toxicity, and you can see the percentage of subjects from 0 to 100 here who had toxicity symptoms from vitamin A alone was quite high, from vitamin D alone was quite high, and no one developed toxicity symptoms when vitamins A and D were provided together. So this seemed to indicate that on the one hand, you need both vitamins together to be effective, and on the other hand, you need both vitamins together to be safe. So this raises the question, how does this synergy happen? And initially thinking about it, you could basically think of two things. Either vitamin A is doing some really cool things, and And vitamin D is doing some really cool different things, and those things that are happening are working together to produce the good clinical outcome. So maybe vitamin A does some things to prevent the common cold, vitamin D does totally different things to prevent the common cold, and when they work together, you get that good result. Alternatively, you could say maybe vitamins A and D actually are needed to work together for the exact same things. Maybe vitamin A and vitamin D don't really do anything unless they're working together. So that's another possibility. And as I'll show you in the following slides, I think it's a little bit of both. So for example, vitamin A is known to independently protect against infection because normally our epithelial barriers, our skin, our mucous membranes, produce mucus-producing cells, and they produce cilia, which are little hair-like structures. And the mucus and the cilia actively work together to clean out infections and to protect our insides from lead and bacteria getting infected. When we have vitamin A deficiency, the cilia, the mucus cells all die, and you get instead an accumulated layer of dead skin cells, basically, called hyperkeratosis. Vitamin A also supports all of these different immune cells and increases the production of zinc-dependent metalloproteinases, which are enzymes that help immune cells dig through tissues to get at the bad guys. And then if we look at vitamin D, this is a complicated chart, but if we just pay attention in the middle, it shows vitamin D binding to its receptor and then producing molecules called cathelicidins, which kill mycobacteria. And then you can see this rest in peace gravestone here, that's the dead mycobacteria. These molecules have also been shown to be protective against Candida, various other types of bacteria, ranging from strep to E. coli, and viruses, to indicate that vitamin A does some independent things, vitamin D does some independent things, and when we have all these working in harmony, we get a beneficial result, protecting us from infections. We I'm going to show you some data that would seem to indicate that it's a little bit more complicated than that, and that we also have other types of synergy. And before we get into that, I'll just give a brief technical introduction to how these vitamins are activated. So vitamins A and D are both prohormones. It's kind of like you imagine you eat tyrosine in your food for protein, and you eat iodine, vitamins A and D. We eat vitamin A, which is called retinol in our food, or vitamin D in our food. And vitamin A gets activated into a two-step process to either all-trans retinoic acid or 9-cis-retinoic acid. These are the hormone forms. And these basically tell our cells what to do, what proteins to make, how much of the proteins to make. Similarly, vitamin D is activated in a two-step process to a compound called calcitriol, which is the activated hormone form. So the hormone forms are all-trans retinoic acid and 9-cis-retinoic acid for vitamin A, and calcitriol for vitamin D. In the last couple decades, we've seen the emergence of very intense understanding of molecular biology, and we now know that vitamins A and D and their activated hormone forms act through nuclear receptors, just like other hormones like thyroid hormone act. And oftentimes these nuclear receptors need to partner up with a different nuclear receptor in order to carry out their functions. And in fact, all of the nuclear hormone receptors, including even those for thyroid hormone, need to partner up with this receptor called RXR, or retinoid X receptor. And as far as we know, 9-cis-retinoic acid, one of the activated hormone forms of vitamin A, is what activates that receptor. So this would seem to indicate that vitamin A is necessary to activate all of the nuclear hormones. And that includes vitamin D. So the activated form of vitamin D binds to its receptor, and it seems we need 9-cis-retinoic acid as a partner. Vitamin A, in its active form, all-trans retinoic acid, also needs 9-cis-retinoic acid as its partner. So what this seems to indicate is that we basically need vitamin A for all of these nuclear hormones to function, including vitamin D. Now there's some controversy over whether 9-cis-retinoic acid even exists. Some scientists argue that it does and some that it doesn't. But I won't get into that because it's too technical. But I'll just say we have a very plausible scenario that would seem to indicate that in order for vitamin D to do anything at all, vitamin A is needed by its side, like their molecular partners. And here's an example where vitamins A and D are working together to tell a cell to make a certain protein. This protein is called osteocalcin. And shown here are a low dose of either vitamin A alone, vitamin D alone, or the two vitamins together. You can see that the two vitamins together gets a huge response compared to the other two. And here is a high dose of vitamin A alone, vitamin D alone, or vitamins A and D together. So you can see that they're cooperating to tell the cell what proteins to make. So if we go back to the models of synergy, it would seem to indicate that this idea that vitamin D does its own independent thing possibly can't even exist, because it may be that vitamin A is needed for vitamin D to function properly, for thyroid hormone to function properly, for basically all of the nuclear hormones to function properly. So maybe, perhaps, what we have is that vitamin A does some independent, really cool things. Vitamin A helps vitamin D do some really cool things, and all of these really cool things work together to get a good clinical outcome, like prevention of the common cold, for example. Of synergy. What are the good models of toxicity? Does vitamin D toxicity work kind of the same way as vitamin A toxicity? We said before, if you have too much vitamin A, not enough vitamin D, you get depressed calcium, and this leads to bone loss. We said before that vitamin D in excessive doses leads to soft tissue calcification. So for example, kidney stones or calcification of the arteries. Is this because you get too much calcium? That would seem to be sort of the reverse of the model for vitamin A toxicity. Well, as it turned out, there seems to be a third interactive partner here. And once we understand the role of vitamin K2 in this process, then we should revise our model for exactly how vitamin D is working. So as it turns out, vitamin K can come in two forms. Vitamin K1 is found in green leafy vegetables for the most part, and vitamin K2 is found in animal products, particularly animal fats or fermented foods. So there are fermented plant products that have vitamin K2, but usually, for example, sauerkraut has very, very little. There's natto, which is a fermented soy product that is popular in eastern Japan. I've never had it, but I've heard it stinks to high heaven. That's actually a really good source. But if you look at goose liver paste, is an excellent source. But if you look at the foods that people commonly eat in our society, eggs and cheese are the main sources. And cheese, because cheese not only is a dairy product of the animal fat, but it's also fermented, so you get that additional vitamin K2 from the fermentation. And so the more fermented it is, the more vitamin K2 you have. So hard cheeses are higher than soft cheeses, for example. And vitamin K1 can actually be converted by animals to vitamin K2. But as it turns out, cows seem to be really good at this, and humans seem to not be so good at all at it. So basically, we're getting most of our vitamin K2 from these animal foods, and we can help assist our vitamin K status by getting the plant foods. Vitamin K activates proteins, primarily by adding carbon dioxide to them. And so, many people don't look at carbon dioxide as a nutrient, but in fact, carbon dioxide is another part of this synergy. And we produce more carbon dioxide when our metabolic rate is higher, because we're basically the opposite of plants. So plants take in carbon dioxide, they metabolize to make sugar and leave off oxygen. We take in oxygen and sugar, and we have our own factories inside, and then we release carbon dioxide. So the vitamin K is not going to work right if the metabolism is plugged up. But that's another story for another time. The key thing here is that vitamin K activates what's called a glutamate residue, which is basically the amino acid glutamate in a protein, and it has one negative charge. Vitamin K adds a second negative charge, and this allows calcium to bind, because calcium has a +2 charge. So these two negative charges bind to the two positive charges, and this gives every vitamin K-dependent protein the ability to bind calcium. Sometimes the calcium just acts as a structural glue. So for example, our clotting proteins that help our blood clot when we have a wound are dependent on vitamin K. And there the calcium just organizes the structure of the protein to give it the right shape. However, vitamin K-dependent proteins also direct calcium in the body from where it shouldn't be to where it should be. So So vitamin D, for example, helps us absorb calcium, but do we want that calcium to wind up in our kidneys as kidney stones, or do we want it to end up in our teeth and our bones as strong bones and teeth? Well, obviously we want strong bones and teeth, and not kidney stones, which are very painful. So we need vitamin K to activate these vitamin K-dependent proteins. As it turns out, many of these vitamin K-dependent proteins are actually regulated cooperatively by vitamins A and D. So vitamins A and D will cooperate to tell a cell to make a certain vitamin K-dependent protein, and then vitamin K will come along and activate it. I showed you before that vitamins A and D cooperate to tell the cell to produce osteocalcin. Osteocalcin is a vitamin K-dependent protein. So vitamin K has to come in and activate that protein in order for it to have any function. Often these proteins will either protect our soft tissues from calcification, or they will mineralize our bones and teeth. And you can see this especially in a protein called matrix GLA protein, which is a vitamin K-dependent protein that is regulated by vitamins A and D. And if you delete the gene that makes that protein entirely from a mouse, they have spontaneous fractures, they have calcified blood vessels, and they're really, really small. So the reason they're really, really small is because our cartilage is a soft tissue that can calcify. And our cartilage is supposed to help us grow, and is supposed to calcify when we're done growing. But what happens in these mice that don't have the vitamin K-dependent proteins is the cartilage calcifies earlier, and they never grow to begin with. So basically, vitamins A of arteries, kidneys, and other soft tissues from calcification to provide adequate growth for children. So that's the synergy. What about revisiting this idea of vitamin D toxicity? Well, I published a hypothesis in 2007 that said basically what's happening in vitamin D toxicity is you're getting a massive imbalance of vitamins A and D, and you're causing a dysregulation in the amount of vitamin K-dependent proteins that are produced. In certain tissues, vitamin D in massive doses will cause vitamin K-dependent proteins to be synthesized at such a great rate that the vitamin K-dependent enzyme can't activate them. So what we get is a bunch of defective proteins. And this was a big harm for the medical industry at one point, because they wanted to genetically engineer cells to produce tons of clotting factors so that they could inject them into people in the emergency room if they were hemorrhaging. But what happened was the cells produced so many of these clotting factors that they were all defective because none of them were being activated. So my hypothesis was basically that when you have way too much vitamin D and way too little vitamin A, instead of just saying it's hypercalcemia, what it is you get overproduction of defective vitamin K-dependent proteins. They can't direct the calcium away from the soft tissues into the bones and teeth, so you get kidney stones, bladder stones, calcified blood vessels, and all these other symptoms of vitamin D toxicity as a result. I sent this hypothesis paper to Zhengdong Ling at Tufts University because his lab in 2007 had recently done a study where they showed that the activated hormone forms of vitamins A and D interacted to protect mice from lung cancer and kidney stones. So what they showed was if you gave the activated hormone form of vitamin D, the mice were protected against lung cancer, but they developed kidney stones. If you gave them both activated hormone forms together, they were still protected against lung cancer, but they did not develop kidney stones. So their study was very in line with what I was looking at that time, showing that the activated hormone form of vitamin A makes vitamin D both safe and effective. So I sent this paper to them, and they investigated the hypothesis in the frozen tissues that they had from that experiment. And what they showed was, this is showing messenger RNA levels of matrix GLA protein, or MGP, that's an important vitamin K-dependent protein. And messenger RNA is basically the intermediate between the gene and the protein. So your gene codes for a protein. This is the message that gets carried from that gene to tell your cell to make that protein. And what happened was, if you gave just retinoic acid, which is the activated form of vitamin A, you didn't get any change in how much this protein was being produced. But if you gave only the activated form of vitamin D, you get a massive increase. And then when you give both vitamins together, the amount you're making normalizes. So this seemed to suggest that if you only have vitamin D alone, the amount you're producing gets out of whack, you're producing way too much, and you can't activate it. Then they looked at the defective and activated proteins. So this is the defective proteins, and they showed that if you just had vitamin A, or you had vitamin A and D together, you had about the same level of defective vitamin K-dependent proteins. But if you only gave the vitamin D alone, you had a massive increase in these defective proteins. When they looked at activated proteins, they showed that if you just gave vitamin A or vitamin D alone, you didn't get any change in the activated protein. But when you gave both of them together, you got a big increase in the activated protein. So this is seeming to show protection against the defective proteins, and also a synergistic increase in the amount of activated protein. Proportion of the total, it was lowest when you had these vitamins together, and it was highest when you just had the vitamin D. So that seemed to support this hypothesis of vitamin D toxicity. So I think we can begin to say that the model looks like you have vitamin A out of balance, you get depressed calcium and bone loss. D out of balance, you get these defective vitamin K-dependent proteins and soft tissue calcification. Now it also seemed to suggest a model of synergy, where when you have vitamins A and D in balance, and you have vitamin K to activate the proteins, you get these activated proteins that produce strong bones and teeth, protect soft tissues from calcification, and provide for adequate growth. There are a few unanswered questions. One is, could we replicate the Tufts study using dietary vitamins instead of the hormone forms? The other is, does vitamin K protect against vitamin D toxicity the same way that vitamin A does? It would seem to be the case, but no one has shown it. I have a postdoctoral research position in Illinois that I'm starting in a couple of weeks, where my project is going to be answering these questions. And if I have a chance, I hope to see if we can investigate this in humans. Before I end, I should point out that there are a couple of other synergistic partners that enter into the equation. One is zinc. Zinc often coordinates the structure of things. This is a zinc finger. Basically, it's a finger shape that fits into certain holes. And these zinc fingers are found in all the nuclear receptors, including those for the fat-soluble vitamins. You can imagine this is just like fitting a key into a lock. If the key isn't the right shape, it's not going to open the door. If you don't have zinc to make the receptor the right shape, it's not going to work. If we look at where zinc is found, we can see that oysters are incredibly high. Ground beef or liver and cheese are also very good sources. Poultry is not as good a source as beef or oysters. Eggs are kind of low, and all of the vegetable products and milk are incredibly low in it. So people who are not eating basically either oysters, meat, or cheese are going to be at risk of not having as much zinc, especially when you consider that plant products have about 5 times lower absorption of zinc. So you can imagine that someone who's not eating any animal products is getting, say, 25 times less zinc than someone who's eating plenty of animal products. The other key factor is magnesium. People often say magnesium interacts with calcium, but in fact, magnesium is just required for everything. Because magnesium is required to make metabolic processes. So really, magnesium is required for everything, and everything completely falls apart when magnesium isn't there. And this is just a brief schematic of how magnesium interacts with calcium, showing that it really isn't a direct interaction, it's just a reflection of the universal importance of magnesium. So ordinarily, vitamin D is activated, is semi-activated, and then fully activated, then stimulates calcium absorption. And parathyroid hormone is secreted from a parathyroid gland to help this activation process continue. And then once we absorb the calcium, we distribute it into our blood, bones, and teeth, and into storage vesicles. Synthesis and secretion of parathyroid hormone, and in the function of parathyroid hormone, and in the function of activated vitamin D, and in all of the pumps and channels that distribute calcium to where it's supposed to go. So if we absorb calcium, we want to get it into our bones and teeth with vitamins A, D, and K and away from our soft tissues. But then we need magnesium to come in and make it go into all the right places, even once it's inside the cell, to go into the right places, rather than accumulating in the places that it doesn't belong.
And when magnesium is not there, you're also not going to get your strong bones and teeth, but you're also going to get all kinds of other problems like involuntary muscle contractions and improper nerve signals. Stephanie had talked a little bit about before about calcium playing that signaling role. So everything goes out of whack with calcium metabolism and magnesium is there. If we look at where we find it in food, it's widely variable within food groups, and you really have to go on the internet and look at a full table to see individual foods. But in general, we can say that most plant foods are rich in magnesium. Seafood is sometimes a good source of magnesium, not always very high. But meat is very low, even liver is very low, and table sugar and rich white flour are terrible sources of magnesium. And if you compare whole wheat to rich white flour, you can see white flour is enriched, but not with magnesium. So that's a serious problem. Protect soft tissues from calcification, provide for active growth, and nourish strong bones and teeth. Vitamin A is found primarily in liver and olive oil, while keratin-rich plant foods can also support vitamin A status because we convert keratins to vitamin A. Vitamin D is found primarily in olive oil and fatted fish, and we can also obtain it from sunshine, although that depends on our skin color, where we live, what clothes we wear, how much time we spend outdoors. Vitamin K2 is found primarily in animal fats, fermented foods, especially egg yolks and hard cheeses. And zinc and magnesium are needed to support all these processes. In order to get them, we need to get both animal products and plant products together to get the balance of minerals that we need. Thank you very much.
Yep.
5
We have
minutes.
5 minutes.
Does heat destroy things too, like keeping your egg yolk and stuff like that? Does that have any effect on that?
The question is, does heat destroy K2? To my knowledge, it doesn't. It might have a small effect, but I don't think it's a major one.
In your research, did you come across the proper or the optimal ratio for AD and K?
The question is there an optimal ratio? I don't think that the question could be, is there an optimal ratio, and then what is it? I doubt that there's an optimal ratio. Probably there's a range of optimal ratios. I really doubt that humans are so, what's the word, precarious. I really doubt that our needs for these vitamins, that our status of balance is so precarious that we need an exact ratio. Probably when the ratio is way thrown off is where you get problems. If there is an optimal ratio, no one knows what it is, despite anyone who tries to claim that they do. And so I think what we would need is more research. What I hope to do in my position is just, first of all, demonstrate, finish off some of the animal research to round out the mechanistic questions, but I'd like to at least do one study in humans showing that this is an important amounts of vitamins that people are consuming. I think once that happens, other researchers will pick up on this once they realize it's relevant. And what we would want to do is have, dose-finding studies where we do a randomized trial of different balances of vitamins A and D to see how they act, what happens to the ratio of vitamin K-dependent proteins in plasma that are activated. For example, that would be one way to start looking at that, and no one's done anything like that. However, I hope that if I can actually get some of this to work and published and people paying attention, I hope that maybe in the next 5 years we can see something like that.
What you were talking about magnesium, so what relationships have you seen through the green vegetables, that are rich in magnesium, eating those, and then there's oxalates, phytates, and other things, goitrogens and things in there. Talk to that a little bit.
The question is, what happens when so many good sources of magnesium have so many bad other things in them? Well, that's a complicated problem because, in most cases, I think a lot of these plant toxins are okay if they're in moderation and the diet's diversified, but you also have people who might be very sensitive to oxalates, and people who might be very sensitive to other things. So I think what you have to do is, I think it can help to diversify the diet so that you're not getting too many negative things from one source. Magnesium is in tons of different foods. It can help to process the nutrients, the foods in ways that neutralize the anti-nutrients. So, for example, seeds and grains can be soaked and sprouted. But you also just have to pay attention to your own individual response to those foods. And if some food is giving you a problem, it could be an allergy, an intolerance, or some exaggerated response to an anti-nutrient, then you just have to try to realize the foods that are giving you a problem and avoid them. However, if you just totally dispense with plant foods because they have anti-nutrients in them in general, you're probably going to wind up deficient in magnesium. You might, I mean, another traditional population that have gotten by on diets that are really low on plant foods, none of them have really done it on purpose, and they're certainly the tail of the distribution. So I think it's a safer approach to try to eat a balance of all those different foods, and if you notice certain things giving you a problem, trying to identify that trigger and get rid of it. Is there in the back?
Yeah, it's been said that really all plants, all vegetables that we would eat are toxic at some point. So we need that diversification because animals, when they eat those things, they detoxify those things, and then when we eat the animal foods, we get those nutrients, that toxicity out of it. So their way of handling that and our way of handling that is to eat a variety of it so that we don't get too much of one thing. If we do eat too much of one thing, like the brassicas, for instance, then that's what's going to happen. I mean, so...
I think the comment was the importance of diversification because all plant foods are toxic. I think there's some truth to that, but sometimes it's not about the amount you consume. So a lot of the goitrogens, for example, iodine protects against them. That's true in the case of crucifers, although there are basically with crucifers, if you're eating 30% of your diet as crucifers, you'd be in serious trouble.
Right.
If you're eating a couple servings a day, one serving a day, you're getting with iodine,
Right.
you're probably protecting
Right.
against it. The other thing you have to consider is that oftentimes toxins are good for you. So the plant, we're well adapted to dealing with plant toxins, and oftentimes we rev up our detoxifying machinery in response to them. And oftentimes the industrial toxins are poorly behaved toxins instead of well-behaved toxins because they don't rev up that detoxifying machinery. So that's a concept called hormesis. And so it's important not to just rely on test tube studies that say, oh, this is a toxin. You also have to look at real studies that feed people foods and see what happens. So it's a really complicated topic. I have, on my website, I have a special report about thyroid toxins that's available for purchase. I've also written some free articles on westingprice.org about crucifers that might be helpful. What do we have for time? Is it over?
I called 5 minutes about
410 preferentially activates the clotting factors, and vitamin K2 preferentially does everything else. However, it's been shown that vitamin K2 in the form of MK7, which is derived from natto as a supplement, activates the clotting factors in people who are on warfarin or related drugs. So vitamin K, too much vitamin K is not going to make you clot too much. But if you have either a genetic predisposition to clotting too much, or if you have a reason that your doctor is trying to make you not clot enough with a drug, then in either of those cases, getting enough vitamin K would subvert what your doctor is trying to do. So, a lot of people who are on warfarin or related drugs are deliberately made deficient in vitamin K, so they get thinner blood and calcified blood vessels and calcified aortic valves. So if your doctor is trying to give you a vitamin K deficiency and you take vitamin K, then you're going to subvert your doctor's ability to give you a vitamin K deficiency. You're not going to get too much clotting just because you're getting too much vitamin K. It's either you don't have enough of the vitamin or you have enough of the vitamin. And that's all that matters for clotting. Now, if you have a genetic issue where you inherently clot too much, then that has to be addressed very carefully, and maybe having a deliberate vitamin K deficiency is something we need to deal with. Although if there's any other way to deal with that, it's preferable because vitamin K does lots of other good stuff.
And so how would you
Realize that the vitamin K, that the drug is going to give you calcification of the aortic valves.
exactly?
And some pharmacists don't even know how the drug acts. I mean, I've talked to people who said that their pharmacist told them that the drug doesn't interfere with the vitamin K recycling enzyme. It inhibits clotting. So, I mean, I don't know how they graduate from pharmacy school, but some people just don't know the information. So I would hope if more doctors knew that those drugs cause calcification of the aortic valves, they would too sweet look for other alternatives. But if you're on the drug, I wouldn't recommend ignoring your doctor or lying to your doctor about getting vitamin K, because if you have clotting issues, you need to manage them appropriately. you don't want to have good bones and teeth and die of a clot. So